take you through buffer calculations that you'll be required to do for OCR F325. Remember that for OCR, a buffer consists of a weak acid and its conjugate base. For this exam syllabus, we don't look at buffers made with ammonia or other solutions like that, so we're only going to concentrate on this one type. So for this, the calculation that you're going to use is the Ka calculation. So we're going to stick with remembering that a buffer equation for us looks like this. Then we'd write our Ka expression and we would rearrange that to give us H+. And so if we were asked to calculate the pH of a buffer solution, then this is the equation we would be using. The other question we might get might talk about relative concentrations or relative proportions. For example, the question might say, calculate the relative proportions that butanoic acid and sodium butanoate need to be mixed in to give a buffer of pH 3.2. And for that you're going to still use this Ka expression, but you're going to rearrange it so that it looks like this. Because this equation is going to give us a ratio, because what we actually want to look at in the end is this, the ratio of salt to acid. So if you get this relative concentration or relative proportion type of question, then this is the equation you're looking at. Both of these are simple rearrangements of the Ka expression. Next, I'm going to give you 10 examples to practice. Pause the video on each one and have a go yourself before you look through the answer. In this next example, we're looking at a buffer made from sodium ethanoate, so that is the salt, and ethanoic acid, so that's our weak acid. We've got a few things in this question, so we've got a molar mass for sodium ethanoate, a volume and a concentration for ethanoic acid, Ka value, and a pH value. Pause the video now and have a go at this question before I go through the answer. So the first thing I'm going to do is I'm going to look at this pH at the end here, and it's fairly easy to pick up marks. If you see a pH, you should always convert that back into H+ concentration using H+ equals 10 to the minus pH, like that, and that gives us a value of 3.16 times 10 to the minus 6, and we'll get 1 mark for doing that. Okay, now we're going to look at the question again, and you might be forgiven for going, well, there's a volume and a concentration there, so I could calculate moles, and under normal circumstances I'd tell you to do that. However, in this question we're not going to get a mark for doing that, so we're going to need to look further at it. So given that it's a buffers question, I'm going to write out the Ka expression. Remember that the only important bit out of sodium ethanoate is the ethanoate ion. The sodium doesn't go into the buffer equation. So that would be our Ka expression. And then we're going to think about things that we can fill in. So actually we've got the concentration for the ethanoic acid, we've got our H+ concentration, and we've got the Ka. So we're going to need to rearrange this to give us ethanoic acid, the ethanoate concentration. So if we look at rearranging this, we're going to get the concentration of the ethanoate ion is equal to Ka times concentration of the acid over the concentration of H+. All we need to do is put the numbers in from up at the top and calculate that, which will give us 0.5696 moles per decimeter. Okay, so concentration of sodium ethanoate will be 0.5696 moles per decimeter. That will definitely be another mark. However, it's asking us for the mass in grams that we're going to dissolve. So if we were going to make up 1 decimetre of sodium methanoate solution, we would dissolve 0.5696 moles. But we're not, so we're making up 500 centimetres cubed, so we're making up half a decimetre. So the next thing we're going to do is halve that number. Okay, so just be clear on that again. If you were making up 1 decimetre of solution, you'd be dissolving 0.5696 moles in 1 decimetre. We're only making up 500 centimetres cubed, which is half a decimetre, so we're only going to need half the amount. Okay, so in that 500 centimetres cubed, we're going to dissolve 0.2848 moles. Maybe get a mark for that. And the final step, it didn't ask us for moles, it asked us for grams, so the mass will be N times MR, which we're given the MR in the question, and that gives us 23.35 grams, and that would be the final mark. In this question, again, we've got volumes and concentrations, and we've been asked to calculate the pH. Pause the video whilst you have a go at this example. Okay, I'm looking at this and I've got a volume and a concentration for lactic acid. So again, look at these questions in terms of what you can do rather than getting overfaced. So if you've got a volume and a concentration, you're going to do N equals CV over 1000. So we've got 0.13 times 85 over 1000. So that is moles of lactic acid. Next, keeping going with the question, got a volume and a concentration for the lactate. So we're going to use the same equation. Okay, back to the question again. I've got a pKa value, so I'm going to need to convert that into Ka. So that gives us 1.26 times 10 to the minus 4. So if I know the moles of each of the solutions, then I'm going to look at what is the volume of the buffer solution. So the volume of the buffer solution, if I've got 85 centimetres cubed of this and 95 centimetres cubed of that, then my total volume is 180 centimetres cubed. And in that 180, I've now got this many moles of that, and that many moles of this in 180. So now I'm going to have to go back into concentrations, because obviously in mixing these two solutions I've changed the concentrations, because I've no longer got 0.13 moles per decimetre, because it was that when it was just in the 85. I've now added an extra 95 centimetres of fluid to that to dilute it. So I'm going to use C equals N times 1000 over V. So let's do that for the lactic acid. And let's also do that for the lactate. Okay, so these are the concentrations that I'm going to use now to calculate the pH of the buffer. So So remember, if you're calculating pH, you use that rearranged Ka expression. So let's sub the numbers in. So we've got Ka, which we worked out up here, concentration of the acid, which we worked out down here, and the concentration of the lactate, which is there. So we've got the concentration of H plus ions. To get the pH, we're going to minus log that number, which gives us a final answer of 4.04. Okay, if you want to run through that again, if we've got a question that involves volumes and concentrations, then immediately you should be thinking CV over 1,000. So we're working out moles of lactic acid. Keep reading the question. pKa, we're going to convert that into Ka. We can't do anything else. You should know that you can convert a pKa value and get at least 1 mark for that. Carry on reading. We've got a volume and a concentration again, so we're going to do moles of the lactate ion. So that gives us these two values here. So we worked out moles of lactic acid and moles of the lactate ion. So we've got 0.01105 moles in 85 centimeters cubed of this lactic acid solution. However, we're diluting that by adding 95 centimeters cubed of something else. So total volume for the buffer is 180 centimeters cubed, because that's 85 plus 95. So then we need to work out the new concentrations after we've mixed these two solutions together. So again, refer back to that AS calculation, rearrange it to concentration equals N times 1,000 over V. Put your numbers in to get the concentration of lactic acid and the concentration of the lactate ion. Now we can go into calculating the pH, so we use that rearranged Ka expression to give us concentration of H plus ions, which gave us this number over here. And then once we've got H plus, we do the minus log calculation to give us the pH. Again, for this type of question, you're looking in the region of 5 to 6 marks on an exam. Quite tricky buffers calculation question. This time you've got some masses and a volume. Pause the video, have a go at this question now. Okay, we're going to start off by reading through this question. First thing we'll come across is pH. So I know that I am going to have to calculate pH for a buffer, which means that I'm going to be using that rearranged Ka expression, which looks like this. So I'm going to bear that in mind for now. Carry on. We've got a mass of the acid. Again, think about, if you look at a question and you don't quite know what to do, look for the things you can do. So if you've got a mass, you can turn it into moles. So we're going to use AS moles calculations again. We're going to do N equals M over MR. So we're going to do 2.2 divided by the MR, which is 122. Again, simple things you can do. If you've not been given the MR in the question, that means you're going to get a mark for working it out. So if you do M over MR for benzoic acid, you get that many moles. And then we're going to carry on through the question. We've got the Ka value, which is good because we're going to need that in this question here. Keep going, we've got another mass, this time of sodium benzoate. So once again we can work out the number of moles. So we do 6.1 divided by the MR of sodium benzoate, which is 144. Again, if you're not given the MR in the question, you'll get a mark for calculating it. So make sure you're doing the straightforward things. And for that we get... Okay, so now we've got moles for each of these. Carry on through the question, and it tells us that they are dissolved in a volume of 500 centimeters cubed, which of course is the same thing as saying 0.5 decimeters. So now we're going to look at the concentration. So we've got for benzoic acid 0.018 moles in 0.5 decimeters. So to get the concentration in moles per decimeter, all we need to do is double it, because we've got half a decimeter, so we need to multiply it to get 1, which gives us that concentration. Do the same for the benzoate ion. So we've got 0.0424 moles in half a decimeter. So to get that into moles per decimeter, we're going to multiply by 2. Which gives us our two concentrations. Then we can substitute everything into this Ka expression. So Ka comes from the question at the top. Concentration of the acid is here. Concentration of the negative ion, the benzoate, is there. And then we need to find an answer. So that's the concentration of H plus ions. The final step is to calculate the pH. So pH, if we've got H plus, we're going to do minus log. Which gives us our pH. So running through this question again, let's put the marks on it. Going through, you're going to get a mark for the moles of benzoic acid. You will probably get a mark for the MR. You're going to get a mark for the moles of sodium benzoate, and possibly a mark for the MR again. You will get a mark for calculating the concentrations, possibly just one for both concentrations. You'll get a mark for calculating the concentration of H plus ions, and a mark for your final pH. So this is quite a high scoring question because there are a lot of steps to it. This question is quite a tricky buffers and weak acids question. Pause the video now and have a go at this question yourself. Okay, now I'm going to go through this question. So we've got 0.02 moles of ethanoic acid in 1 decimeter, which means that the concentration is 0.02 moles per decimeter. Watch out for this volume not being a decimeter, so that you would have to do something with this number of moles. Carrying on reading through the question, we've got a pKa, which means that for us we're going to turn that into Ka by doing 10 to the minus 4.8, which gives us 1.58 times 10 to the minus 5. And if this were an exam, we would get a mark for that number. Then we're going to come down to the rest of the question. So it's asking us to calculate the pH. We'll notice in part A that we've been asked about ethanoic acid. There is no mention of a salt or a conjugate base, so this part of the question is about a weak acid. If we've got a weak acid and we want to find the pH, then we use the square root equation to find the concentration of H+. So all we need to do is substitute the numbers into that equation. So that's our concentration of H+ ions. Again, we'll get 1 mark here. Final step in part A. To get the pH, we're going to do minus log of that number, which gives us a final answer to part A of pH 3.25. And we'll get a mark for that answer as well. Coming down to part B then, what we're doing now is adding sodium hydroxide. So we're doing something to the acid. So let's have a look at the equation. We've got ethanoic acid, and that's reacting with sodium hydroxide. So we've got an acid-alkali reaction, which will give us a salt, which will be sodium ethanoate, and some water. We know then that we are adding 0.008 moles of sodium hydroxide. We know that we started with 0.02 moles of ethanoic acid. If we nominally say that we're going to use 1 decimeter cubed, we can stick with those numbers. So then we're going to look at the ratios. So 1 lot of sodium hydroxide produces 1 lot of sodium ethanoate. So in theory, we should get this many moles of sodium ethanoate. Then we look at the ethanoic acid. If it's going to react with 0.008 moles of sodium hydroxide, we need to find out what's left. So we take those two numbers away from each other, giving us a final number of 0.012 moles per decimeter for the ethanoic acid. Then, carrying on looking at the question, so it's asking us what is the pH. We know that part B is a buffers question, and if it asks us about the pH, then we are going to use that rearranged Ka expression. Again, all we need to do now is substitute the numbers in. So Ka is exactly the same as it was at the top of this question. We just calculated the concentration of the ethanoic acid, and we've also calculated the concentration of the ethanoate ion. So that is our concentration of H+ ions, so we should get a mark here for this, possibly 1 for calculation of these concentrations. Final step, pH of the buffer, I'm going to do minus log of that answer. Gives us a final pH of 4.63. If your answer is slightly different to mine, that's because you might have rounded somewhere in the calculation. Try and leave your rounding until the very end. In this example, we're looking at a buffer made from nitrous acid and sodium nitrite, and we're looking at buffering at pH 3.55. Pause the video now whilst you have a go at it before I go through the answer. Okay, so first thing we're going to look at in this is what the buffer actually is. So this is nitrous acid. You might be fooled into quickly reading that and thinking it's nitric, which is strong, but it's not, it's nitrous. So this is our weak acid. So the buffer system that we're dealing with is this one. Okay, you won't need that equation really for answering this question, but it's just for clarity on what we're talking about. So this is asking us about what volumes should we be mixing. So this should be directing you to that ratio equation where we've rearranged the Ka expression so that it looks slightly different to what we're expecting. So it now looks like this. Remember, in previous videos, previous examples, we've talked about the fact that if you get a question that says what relative concentrations or what volumes or what ratio should the salt and the acid be mixed in, then we're talking about this ratio equation. Now the straightforward thing we're going to do is substitute the numbers into there, but before we get to that, we need to convert this pH into an H+ value. So concentration of H+, we do 10 to the minus pH which gives us a concentration of 2.818 times 10 to the minus 4 moles per decimeter. Okay, so remember again, if you get a Buffers question like this, you can't think of anything else to do, but you see a pH, turn it into H+, because there will always be a mark for doing that. Then we can go back over to this rearranged Ka expression and put the numbers into that. We've got 4 times 10 to the minus 4 divided by that concentration that we've just worked out, gives us a ratio of 1.42 to 1 essentially. So what that says is concentration of A minus to HA is 1.42 to 1. Now if I want to make up 1 decimeter of this, then I'm going to say, right, well, in total I've got 2.42, so I'm going to do 1 decimeter is 1000 centimeters cubed divided by 2.42, and I'm going to times that by 1.42 to tell me what the 1.42 is, which gives me 587, I'm going to round it up, centimeters cubed of the sodium nitrite solution. So if I'm making up 1 decimeter cubed, then I'm going to work out how much of the nitrous acid I need. So that's going to be, take away that, gives me 413 centimeters cubed of the HNO2 solution. And that would be our final answer. This question, we've got a buffer made from propanoic acid. Pause the video and have a go at this question. Okay, so when we're looking at this question, a couple of things we're going to do. First of those is to convert this pKa value into a Ka value, so we're going to do 10 to the minus 4.8. So that's our Ka value. Remember to leave that in your calculator until you do your next calculation, don't round until the end. If this was a mark scheme, you get 1 mark for your Ka value. Next thing to notice is that instead of concentrations, we've been given moles of the acid and its conjugate base. And we've got a volume. So we need to convert these from moles into moles per decimeter or concentrations. So if I'm thinking I've got 0.11 moles in 1.5 decimeters, how many have I got in 1 decimeter? So I'm going to divide that number by 1.5, and I'm also going to do that to the conjugate base. Okay, so now we've got our 2 concentrations for the acid and its conjugate base. These are in moles per decimeter. Next thing we're going to do, it tells us to calculate the pH of the buffer. If we're going to calculate the pH of the buffer, then we're going to be using the Ka expression and we're going to rearrange it to give us H+. Next we're going to put the numbers in. So again, you should have left this in your calculator from earlier, so you shouldn't be introducing rounding errors. Concentration of the acid was up here. Concentration of the conjugate base is there. So now we've got our concentration of H+ ions. Again, we should get 1 mark there. Final step, calculate pH using minus log. gives us 5.13, and that should be our final answer. In this question, we've got some data about a buffer made using butanoic acid, and the question is asking us to calculate the pH of the buffer. Pause the video now whilst you have a go at this question. Okay, so we're going to start off with that Ka expression again. So in this case, I'm not going to use HA because I've been told that it's butanoic acid. So my Ka expression would look like this. I'm going to need to rearrange this to give me H+. That's the equation that I'm going to use for this calculation. Then I just need to put the numbers in. Concentration of butanoic acid is up here, and the concentration of sodium butanoate is there. So that's the concentration of H+ ions that we should find. Once you've got the concentration of H+, it's asking for the pH, so the second part of this calculation will involve doing minus log. Remember not to round your answer until you get to the end, so leave that answer in your calculator when you minus log it. You should get a pH of 4.52. Things to notice about this question: although it gave us volumes, we didn't need them for this question. They were just to throw us off what we were actually supposed to be doing. This question gives us some data about a buffer made using lactic acid. We've got a pKa value and some concentrations, and again it's telling us to calculate the pH of the buffer. Pause the video and have a go at this question. Okay, first thing we're going to do is we're going to convert this pKa value into a Ka value, so we're going to do 10 to the minus 3.9. Gives us a Ka value of 1.259 times 10 to the minus 4. Remember not to round this, leave it in your calculator whilst you go through the rest of the calculation. Next thing, if we're being asked to calculate the pH, then we know that we're using the Ka expression, but we need to rearrange that to give us H+. Then we need to put the numbers in, so Ka we just worked out. We've got the concentration of the acid, that's up here, and the concentration of the sodium lactate, that's there. Should give us an answer of so 1.68 times 10 to the minus 4. Again, leave this in your calculator, don't round it until the very end. So that's moles per decimeter of H+. If you were getting this as an exam question, you'd be having 1 mark for your Ka value, 1 mark for your H+ concentration. Once we've got the concentration of H+ ions, we can put that into the minus log calculation to get the pH. Which gives us a pH of 3.78. which would be an extra mark on a mark scheme. Just remember, when you're looking at this type of question, even though it says sodium lactate, really what we're talking about is the lactate ion. The sodium is largely irrelevant to our question.